Have you ever found yourself straining to hear a faint radio signal? Or maybe your phone is just, well, utterly struggling to find a solid connection in a weak service area. Perhaps you've tried to stream a weak satellite broadcast and all you get is static. We've all been there, right?
Yeah.
That frustration, it's the constant, often silent battle against an invisible foe we call noise. It's that unwanted guest that always seems to show up, obscuring the crucial information we desperately want to receive. Imagine for a moment trying to have a really important conversation with a friend in a packed, incredibly noisy restaurant. Your friend's voice. That's our signal. And all the clatter, the chatter, the clinking of glasses around you, that's the noise. How on earth do engineers manage to design systems that allow us to hear that critical conversation, that vital signal, even when the restaurant, or, the electromagnetic environment, is overwhelmingly loud? Well, this deep dive is all about pulling back the curtain on a truly critical, yet often overlooked, parameter known as noise figure. This metric, it quantifies just how much unwanted noise a component or system adds to a signal. We're going to explore exactly what it is, why it's so incredibly important in everything from your home Wi-Fi router to the incredible feats of deep space communication, and fascinatingly how we actually go about measuring something that is, by its very nature, an unwanted disruption.
And our mission for you, our dedicated listener, is this. By the end of this deep dive, you won't just conceptually understand what noise figure is. You'll grasp its profound, fundamental impact on the design of entire systems, on their sensitivity, that is, their ability to pick up even the weakest signals, and ultimately, their reliability in the complex, high-stakes world of RF and microwave systems. We're going to delve into its very origins, understand how it propagates through circuits, and unveil the ingenious methods engineers employ to keep this silent killer of signals firmly in check.
To guide us on this journey, we've been immersing ourselves in a comprehensive and truly foundational application note titled Fundamentals of RF and Microwave Noise Figure Measurements. It has provided us with a rich, factual, and incredibly detailed bedrock for this entire discussion, and we're excited to share its insights with you. Okay, let's unpack this. We've used the term noise quite a bit already. But what exactly is noise in this specific RF and microwave context, and why is it such an immense problem, especially for modern receiving systems that are designed to process incredibly weak signals, often, barely above the background chatter?
That's a crucial distinction to make right at the start. In this field, noise primarily refers to spontaneous random fluctuations in electrical current or voltage. These fluctuations are inherently caused by the ordinary physical phenomena within electrical equipment itself. It's sort of the unavoidable electrical fizz of components. This is really distinct from human-generated interference like ignition sparks from an engine or electrical storms in the atmosphere or even spurious signals picked up from nearby equipment. While those are definitely also unwanted, this deep dive focuses specifically on the intrinsic, internally generated noise that's always present no matter what.
Okay, so it's not the external stuff, it's the stuff the system itself creates. Got it.
Exactly. And the problem with this internal spontaneous noise is profound. As a weak signal travels through the various components of a receiving system, maybe an amplifier, a mixer, or a filter, each and every one of those components adds its own little bit of noise. This added noise then begins to obscure the already faint signal. And here's the kicker. Once this unwanted noise has joined the legitimate signal within the same frequency band, the system's components can no longer tell them apart. They become completely inseparable. From that point on, if you try to boost the signal's level by applying more gain, you're not just amplifying the desired signal, you're also raising the noise level by an equal amount. The relative degradation in signal quality has already happened and is now, well, baked in.
Baked in. That paints a clear picture of why this invisible foe is so problematic. So with noise being this insidious and unavoidable part of any electronic system, engineers obviously need a way to quantify its impact. And that's precisely where noise figure, or NF, comes in. It's a crucial metric, standing alongside other key system parameters like sensitivity, which tells us, how weak a signal or receiver can detect, and the bit error ratio, or BER, which measures the number of incorrect bits received in a digital communication system.
Exactly. And noise figure offers a unique and incredibly powerful advantage over those other parameters. While sensitivity and BER are excellent for characterizing an entire receiving system, noise figure can do that and characterize individual components within that system. Think about it. You can measure the NF of a preamplifier, a mixer, or an intermediate frequency, or IF amplifier totally in isolation.
So it's more granular. You can pinpoint the noisy parts.
Precisely. This granular capability means that by carefully controlling the noise figure and the gain of each individual component, designers have direct control over the noise figure of the overall system. And once a system's noise figure is known, its sensitivity can be estimated quite easily, especially when you factor in the system's operational bandwidth.
So the real power of noise figure isn't just that it characterizes a system, but that it helps engineers figure out where the noise is being introduced and by how much, right down to the component level. That kind of insight must really help differentiate one amplifier from another, or even one transistor from another.
Oh, absolutely. This widespread application of NF specifications highlights just how vital it is to have highly repeatable and incredibly accurate measurements, especially when you're talking about components and systems being exchanged between suppliers and their customers. Everyone needs to be on the same page.
Right. You need that common yardstick.
It's an economic and engineering imperative, really. When faced with the challenge of overcoming noise, there are two main approaches. The first is to try and make the weak signal stronger. This could involve substantially raising the signal power transmitted from the source, or increasing the amount of power the receiving antenna can intercept, maybe by simply making the antenna much larger, thereby increasing its aperture or gain. However, these methods often run into significant limitations. Government regulations might restrict transmit power. Engineering constraints can make certain antenna sizes just impractical, or very often the sheer economics of the situation, like the prohibitive cost of building massive antennas, make these approaches unfeasible beyond a certain point.
Okay, so making the signal louder isn't always practical or even possible. That's where minimizing the internal noise becomes such a powerful lever, right? The application note gives a fantastic concrete example in satellite systems. It says in a direct broadcast satellite, or DBS, receiver, simply lowering the receiver noise figure by just 1 dB, just one, can have approximately the same beneficial effect on the signal as increasing the receiving antenna's diameter by a whopping 40%. That's huge. Think about the massive cost implications on a production line. If you can achieve that 1 dB reduction through careful component selection, maybe fine-tuning impedance levels or adjusting specific transistors, rather than having to physically redesign and produce significantly larger or more expensive antennas and their supporting structures, the savings must be astronomical.
Exactly. The cost-benefit of improving noise figure can be immense. And it's not just about receivers either. Noise figure also has relevance in transmitter design. For example, if you're using a linear broadband power amplifier in, say, a base station, any excess broadband noise generated by that amplifier could actually degrade the signal-to-noise ratio in adjacent channels. This could severely limit the overall effectiveness of the entire system. So, measuring the noise figure of such a power amplifier provides a clear figure of merit, ensuring acceptable noise levels before it's even integrated into the live system.
Okay, so just to distill this critical point, lowering the receiver noise figure has the exact same beneficial impact on the output signal-to-noise ratio as improving any other quantity that contributes to that ratio. We're talking transmitted power, the gain of the antenna, or even like the atmospheric transmission coefficient. It's all about making that conversation in the noisy restaurant clearer, isn't it?
That's a perfect way to put it. It's another tool, and often a very cost-effective one, in the engineer's toolbox for improving that final signal quality.
All right, if we're going to effectively fight this invisible foe, noise, we absolutely need to know its roots. From a physics perspective, what are the fundamental sources of these spontaneous electrical fluctuations that plague our RF and microwave systems? Where does it actually come from?
Understanding the genesis of noise is definitely crucial for combating it effectively. One of the most fundamental sources is thermal noise, often called Johnson noise, or sometimes Johnson-Nyquist noise. This type of noise arises from the completely random, spontaneous vibrations of conduction electrons in holes within any conductor, simply due to their finite temperature. Imagine tiny particles constantly jiggling around inside a wire because it's not at absolute zero temperature. Some of these random movements will, just by pure chance, generate tiny electrical currents. And if the spectral content of those currents falls within the specific frequency band we're interested in, well, they contribute to the overall noise floor.
So it's basically the heat energy making electrons wobble randomly.
In essence, yes. And what's key about thermal noise is its nearly uniform spectral content across the entire RF and microwave frequency range. It has an almost flat power density. The available power that a thermal source can deliver into an impedance-matched load can be precisely calculated by the formula kTb watts. Here, K is Boltzmann's constant, a very, very small number. T is the temperature of the source in Kelvin, that's the absolute temperature scale, and B is the system's noise bandwidth in Hertz. The crucial implication for engineers is that this available power is entirely independent of the source impedance itself. Double the bandwidth, you double the available noise power. Double the absolute temperature, you double the noise power.
Okay, thermal noise. Got it. What else?
Then we have shot noise. This originates from the quantized nature of current flow. Electrical current isn't a continuous, perfectly smooth stream like water from a tap. It's actually a flow of discrete charge carriers, individual electrons. These discrete movements, happening randomly in time, create tiny fluctuations that manifest as shot noise. It's like the sound of rain on a tin roof, individual drops making up the overall noise. Similar to thermal noise, there are other quantized phenomena in nature that also produce noise in a similar manner, particularly in semiconductors. Examples include the generation and recombination of electron-hole pairs, which gives rise to something called GR noise, and the division of emitter current between the base and collector in transistors, known as partition noise. Like thermal noise, these mechanisms also produce frequency spectra that are essentially uniform, contributing equal power density across the RF and microwave range, so they just add to that flat noise floor.
It's fascinating that the concept of noise temperature you mentioned earlier doesn't always directly equate to a device's physical temperature. Can you clarify that for us? It sounds a bit counterintuitive that a device could have a high noise temperature but feel, cool to the touch.
It can indeed seem that way at first. When we refer to a device as having a specific noise temperature, we don't necessarily mean that the component itself is physically sitting at that exact temperature. Instead, it means that the noise power it generates is equivalent to the noise power that would be produced by a perfectly thermal source, like a resistor, held at that specific temperature. It's an equivalent measure, a way of quantifying the noise it adds in familiar temperature terms, rather than an absolute physical temperature reading. However, it's worth noting that there can still be a dependence on physical temperature. For instance, some of the very lowest noise figures, which are highly desirable in ultra-sensitive systems like radio astronomy, can only be achieved by physically cooling the device, particularly the first amplifier stage, to a temperature significantly below ambient room temperature, often down to cryogenic levels using liquid helium or nitrogen.
So cooling it down literally reduces the jiggling and thus the thermal noise.
Exactly. It quiets down those random electron movements. Now, it's also important to reiterate that the application note we're digging into focuses very specifically on spontaneous noise, the noise generated internally by the physics we just discussed. It explicitly excludes human-generated interference, which, while critically important for receiving weak signals in the real world, isn't what we're measuring when we talk about noise figure. So we're not talking about noise from car ignition systems, electrical sparks from machinery, or unwanted pickup of spurious signals from other transmitters. Nor are we concerned with erratic natural disturbances like electrical storms in the atmosphere. Those types of problems are typically solved through different techniques, things like relocating equipment, applying robust filtering, or ensuring proper electromagnetic shielding.
That's a good distinction. But why mention these external sources if they're excluded from our definition of noise for measurement purposes? It almost seems counterproductive to bring them up if we're not focusing on them.
But they're mentioned because, paradoxically, these external sources, even though they aren't the type of noise we're characterizing, are incredibly important in one specific sense. They can completely upset the measurements of the spontaneous noise that we are concerned with. For example, imagine a manufacturer trying to measure the noise figure of a very sensitive low-noise amplifier, an LNA. They might find it incredibly difficult because there is a powerful mobile phone base station nearby radiating RF power at the very frequencies they're trying to measure. This external interference swamps the subtle internal noise of their LNA, making an accurate measurement nearly impossible. For this very reason, precise noise figure measurements, especially for low-noise devices, are often performed in specially constructed shielded rooms, Faraday cages to block out all external interference, ensuring only the device's intrinsic noise is measured.
Right, so you have to isolate the device from the noisy outside world to hear its own internal whisper. Makes sense. Okay, so we understand the origins of noise, the internal stuff we care about. Now let's go back to the source, to the 1940s, and to the pioneering work of Harold Freese at Bell Labs. How did he define noise figure, and why was that definition so insightful and, well, ultimately enduring?
Harold Freese, back in the 1940s, provided what has really become the foundational and most basic definition of noise figure. It's elegant in its simplicity. He defined the noise factor, which he denoted as F, of a network as the ratio of the signal-to-noise power ratio at its input to the signal-to-noise power ratio at its output. So SN in, SN out. What's truly insightful here is how he framed it. The noise figure of a network is essentially the decrease or degradation in the signal-to-noise ratio as that signal passes through the network. It's a measure of how much worse the signal quality gets.
Degradation. Okay, so a
Or-
perfect device wouldn't degrade it at all.
Precisely. Think of it this way. A truly perfect, ideal amplifier would simply amplify the noise that's already present at its input, often thermal noise from the source driving it along with the signal, by the exact same amount. It would therefore maintain an identical signal-to-noise ratio at both its input and its output. Its noise factor, F, would be 1 or 0 dB. However, a realistic amplifier, the kind we actually build, will always add some extra noise from its own internal components, those thermal and shot noise effects we just discussed. And it's this added noise that causes the signal-to-noise ratio at the output to be lower than at the input. It degrades the ratio. So a low noise figure, 1 close to 1 or 0 dB, fundamentally means that the network adds very little of its own unwanted noise, making it a cleaner amplifier or network in general.
That really brings the core idea home. A perfect amplifier just does its job without introducing extra mess, but a real-world one inevitably contributes some noise. A low noise figure, then, means a highly efficient, very clean amplifier.
Exactly. Now, it's also important to clarify what noise figure doesn't characterize, because sometimes there's confusion. Noise figure applies specifically to networks that process signals and have at least one input and one output port. We typically discuss it in the context of two-port networks, which are devices with a distinct input and output, like amplifiers or filters, even mixers, which are generally three-port devices with an RF input and LO input for the local oscillator and an IF output for the intermediate frequency, are usually treated as two-port devices for noise figure analysis. The local oscillator is connected to its dedicated port, and we look at the signal path from RF input to IF output.
So it's for things that process a signal through them.
Right. However, noise figure is not a quality factor for one-port networks, such as simple terminations or resistors. It's also not used for oscillators. Oscillators have their own specific quality factors, like carrier-to-noise ratio and phase noise, which describes the short-term fluctuations in an oscillator's frequency to characterize their performance. Although it's worth noting that noise generated in the sidebands of a local oscillator driving a mixer can certainly add to the system's noise and increase the overall noise figure of a receiver. But the noise figure metric itself doesn't characterize the oscillator directly. Furthermore, noise figure has no bearing on modulation or demodulation schemes. It's independent of the modulation format, like AM, FM, QPSK, and the fidelity of modulators and demodulators. This makes it a more general, fundamental concept than sensitivity measures specific to certain communication types, such as noise quieting for FM receivers or bit error ratio, BER, for digital communications. Noise figure sits underneath those system-level specs.
Right, it's a more fundamental property of the hardware itself. And you mentioned earlier, it's interesting how this measure is fundamentally about the degradation of the signal-to-noise ratio, regardless of any subsequent amplification. Can we just confirm that once noise has been added to the signal by a component, any subsequent gain in later stages simply amplifies both the signal and the noise together, meaning it doesn't actually change the signal-to-noise ratio itself. The degradation is already locked in, right?
You've hit on a core truth there. Once that internal noise is introduced and mixed with the signal, applying more gain down the line doesn't improve the fundamental signal quality. It just boosts the signal and the accompanying noise proportionally. The ratio stays the same. Let's make this even more concrete with an example, similar to what's described in our sources factor 1 to 2. Imagine an amplifier's input, where our desired signal is, say, a robust 40 dB above the inherent noise floor. That's a very good starting point. Now, as that signal and its accompanying input noise pass through the amplifier, two things happen. First, the amplifier provides its specified gain. Let's say it's a 20 dB gain amplifier. So the signal gets boosted by 20 dB, and critically, the input noise also gets boosted by that same 20 dB. But then, the amplifier, being a real-world device, adds its own internal noise on top of that amplified input noise. As a result, at the amplifier's output, our signal might now only be 30 dBs above the new, higher noise floor.
Ah, okay, so it started 40 dB clear, got boosted, but the amplifier's own noise filled the gap somewhat, leaving it only 30 dB clear.
Precisely. And if the signal started 40 dBs above the noise, and now it's only 30 dBs above the noise, that means there's been a degradation of 10 dB in the signal-to-noise ratio. This degradation directly tells us that the amplifier has a 10 dB noise figure. It's that simple, conceptually.
And what's really important for engineers, I guess, is that this measurement is independent of the input signal level, right? Like if that input signal had been 5 dBs lower, say 35 dBs above the noise floor, it would still degrade by 10 dBs, so the output would be 25 dBs above the noise floor, and the noise figure would still remain 10 dBs, assuming it's operating linearly, of course.
Exactly right. This independence from input signal level, as long as the device remains in its linear operating region, is one of its powerful attributes as a device characteristic. Now, there's a subtle but absolutely critical effect we need to touch on. The degradation in a network's signal-to-noise ratio, the noise figure, is actually dependent on the temperature of the source that is exciting that network. The noise coming in affects the measured degradation. To standardize measurements and allow for meaningful comparisons between different devices measured in different labs, Priest suggested a standard reference source temperature of 290 Kelvin. This temperature, which is equivalent to about 16.8 degrees Celsius or 62.3 degrees Fahrenheit, was chosen because it's reasonably close to the average ambient temperature seen by receiving antennas in many terrestrial applications, looking across the atmosphere.
So 290 K is the magic number for defining noise figure.
It is the standard reference, yes. The standard reference temperature, T0, T0, or T0, is crucial. The available thermal noise power spectral density for KT0 is a very specific value, 4.00 by 1021 watts per hertz, or in units often used by engineers, that's Nagish 174 dBm per hertz. This value essentially defines the reference thermal noise power available per unit bandwidth at the standard temperature. The IRE, the Institute of Radio Engineers, which was the forerunner of the modern IE, Institute of Electrical and Electronics Engineers, officially accepted 290 Kelvin as the standard temperature for determining noise figure back in the 1950s. This means that the formal IE standard definition states that noise figure, or noise factor F, is the ratio of the total noise power output of the device to that portion of the noise power output that is due solely to the thermal noise at the input when that input source temperature is exactly 290 Kelvin.
Okay, it's quite precise. So just to be super clear on the terminology, we might hear noise factor or noise figure in linear terms for F, but modern usage of noise figure NF almost always refers to that value expressed in decibels, dB, and L equals 10 log. Is that right?
That's spot on. The decibel, or dB representation, is far more common in practical engineering discussions and datasheets. It directly relates to power ratios on a logarithmic scale, making it much easier to conceptualize system performance changes, and for doing quick mental arithmetic in the lab. A 3 dB noise figure means the SN ratio is halved. A 10 dBb noise figure means it's reduced by a factor of 10. It's very intuitive in dB.
Earlier, you mentioned noise temperature, and now we've established the standard reference temperature, T0, for noise figure. How does this other concept, effective input noise temperature, often denoted as T, relate to noise figure? And when would a designer prefer to use one over the other?
That's a great question. Effective input noise temperature, T, offers an alternative but closely related way to characterize devices' noise performance. It's particularly intuitive in certain applications. T is defined as the equivalent temperature of a hypothetical noise source connected to the input of a perfect, completely noise-free version of the device that would produce the same amount of added noise power at the output as the actual real-world device produces. It's essentially asking, how hot would the input source need to be to account for the noise this device adds if the device itself were perfect? It's directly related to the noise factor F by a simple equation. T equals T0, F1, where T0 is our standard 290 Kelvin.
So F1 means T0. A noiseless device has zero effective input noise temperature.
Exactly. And this metric, Taylor, is particularly prevalent in the design of satellite communication receivers and radio astronomy systems. Why? Well, in terrestrial VHF and microwave communications, the input noise levels coming from the antenna are often quite close to that 290 Kelvin reference temperature, mainly due to the thermal radiation from the Earth's surface and lower atmosphere. In such cases, a 3 dB change in the receiver's noise figure typically results in a corresponding, fairly predictable 3 dB change in the overall signal-to-noise ratio. However, in satellite systems, the antenna is often pointed up towards space. The noise level originating from the antenna can be significantly lower, sometimes limited mainly by side lobe radiation picking up ground noise, but often dominated by the very cold background sky temperature, which can frequently be below 100 Kelvin, sometimes much lower.
Ah, okay. So if the actual input noise is way below 290 K, the standard noise figure definition, while still technically valid, might not feel as directly relevant to the actual performance change.
That's the practical difference, yes. In those very cold antenna scenarios, a 3 dB change in the receiver's noise figure could result in a much greater than 3 dB change in the signal-to-noise ratio at the output. The impact is amplified because the device's noise is being compared to a much quieter input. This makes Te a preferred system parameter for many designers in these fields because it more directly reflects the impact of device noise relative to those low noise input conditions. The sources figure 1 to 3 really helps visualize this. It shows plots of how the degradation in SN ratio varies with Te for different actual source impedance temperatures, really emphasizing how NF is specifically defined only for the case where T is equals 290K. Te gives you a value that's independent of that assumption.
Got it. So Te is particularly useful when your real-world input isn't close to that standard 290K. Makes sense.
Precisely. Now, most real-world systems aren't just one component, right? They're a chain, a cascade of amplifiers, mixers, filters, maybe attenuators. This leads to our next challenge. How do we figure out the overall noise figure of a complex system with multiple stages, each adding its own little bit of noise?
Yeah, how does noise stack up as it goes through the chain?
That's where the cascade effect comes in. And it's a truly fundamental concept in RF system design. The good news is that the overall noise figure of a multi-stage system can be calculated if you know the individual noise figures and, crucially, the gains of each component in the chain. The process involves determining the internal noise added by each stage, which we can relate to its individual noise figure and its associated gain. The cornerstone for this calculation is another contribution from Harold Freese, Freese's cascade noise equation. This equation looks a bit intimidating at first, but the concept is powerful. It shows that the total system noise factor, Freese's, is a sum. It starts with the noise factor of the first stage, F1. Then you add the noise contribution of the second stage, which is F21, divided by the gain of the first stage, G1. Then you add the third stage's contribution, F31, divided by the product of the gains of the first and second stages, G1, G2, and so on down the chain.
Okay, that equation definitely looks like something engineers use calculators for. But what's the absolute most important takeaway from it for system designers? If I only remember one thing about how noise propagates through multiple stages, what should it be?
The single most crucial insight, the one that drives so much of low noise design, is this. The noise contribution of later stages in the cascade becomes less significant if the gain of the preceding stage, or stages, is high. Look at that equation. F2's contribution is divided by G1, F3's by G1, G2. This is precisely why the preamplifier gain, the gain of the very first active stage in a receiver, is an absolutely critically important parameter in receiver design for minimizing the overall system noise figure.
Right, because if G1 is large, it shrinks the impact of F2, F3, and everything that comes after.
Exactly. Think back to our noisy restaurant analogy. If your friend, the signal, can shout loudly enough right at the beginning, high gain in the first stage, to be clearly heard over the immediate table chatter, first stage noise, then the background noise from the rest of the restaurant, later stage noise contributions divided by that initial shout, becomes much less of a problem for your overall conversation. You want a high gain, low noise first stage to effectively set the noise floor for the rest of the system. Its performance disproportionately affects the final outcome.
That makes perfect sense. Maximize gain early, while keeping that first stage low noise, of course, to diminish the impact of later, possibly noisier stages. Now, gain is obviously important, but our source material talks about different types of gain and the complexities of something called mismatch. Can you clarify these terms for us? It sounds like there's more to gain than just, amplification.
You're absolutely right. Gain isn't a single monolithic concept in RF, and mismatch adds significant complexity, especially when cascading components. First, let's remember, when we discuss an input noise power like KTB, we're talking about available power. That's the maximum power that a source could deliver to a perfectly matched load. If a device, particularly something like a low-noise amplifier designed for optimum noise performance, has a significant input mismatch, meaning its input impedance isn't perfectly matched to the source impedance, usually 50 ohms, then the actual power delivered into the device will be less than the available power due to reflections.
Okay, so mismatch means not all the power gets in.
Correct. This leads to different definitions of gain, depending on what you're accounting for. Transducer gain, GT, is the ratio of the actual power delivered to the load to the maximum power available from the source. This definition implicitly accounts for any input mismatch loss. It's often what you measure in a real system. Then there's available gain. This is the gain that results when a specific source admittance drives the device and the output is conjugately matched to the load to extract maximum power. This is often a parameter provided for individual transistors in their datasheets and is crucial for amplifier design calculations, as it represents the best possible power gain under specific matching conditions. Finally, insertion gain, G, or more commonly in S parameter terms, the squared magnitude of the forward transmission coefficient, which is S212, is the most common gain measured or specified in typical 50 ohm systems. It essentially measures how much power gets through the device from input to output when both source and load are the standard system impedance, like 50 ohms. S21, part of a device's S parameters, characterizes this forward transmission.
Okay, different ways to define gain depending on matching. And what about these mismatch errors in cascades?
Right. In cascaded devices, if the output impedance of one stage doesn't perfectly match the input impedance of the next stage, the total gain of the series doesn't simply equal the product of the individual stage gains, like S212 values. There are reflections and interactions between the stages. But mismatch can also do something even more complex and subtle when it comes to noise. It can actually alter the amount of noise generated within a subsequent stage itself, not just how much signal power gets transferred between them. The impedance presented to a stage influences its internal noise generation.
That sounds incredibly complicated.
Yeah.
Why is this mismatch effect on noise so hard to correct for then? It seems like something we should be able to model if we know the impedances.
It's hard because a complete analysis of these mismatch effects in noise calculations is quite lengthy and mathematically intricate. It requires a deep understanding of how the noise figure itself depends on the source impedance presented to the device at its input. While S-parameter correction, which characterizes how power flows and reflects, is incredibly useful for correcting gain measurements due to mismatch, it's often not sufficient for fully optimizing or accurately correcting the noise figure. This is because standard S-parameters don't fully capture how that source impedance influences the fundamental noise generation processes within the device itself. You need more information.
This raises an important question then. If a simple noise figure measurement, especially in a mismatched system, isn't enough to fully characterize a device's noise behavior, what are these noise parameters you alluded to? What additional information do they provide?
That's an excellent lead-in. Noise figure, while incredibly useful as a single metric under standard conditions, 290K source, usually matched, is in principle a simplified model of a more complex reality. Real-world amplifying devices like transistors often have multiple internal noise contributors, thermal, shot, partition noise, maybe others, and the way these are generated and combined is intricately influenced by the complex source impedance presented to the device's input. The noise figure you actually measure is impacted by the match of both the noise source you use and the measuring instrument connected to the output. To address this complexity and provide a more complete picture, especially for device designers, we use noise parameters. There are typically 4, but often represented as 3 key values. Vemin, or opt, gamma opt, and RRN-FEM is the minimum noise factor, or minimum noise figure in dB, that the device is intrinsically capable of achieving. It's the absolute best noise performance possible under ideal source matching conditions. Pairopt, gamma opt, is the optimum source reflection coefficient, essentially the specific complex input impedance match at which that minimum noise factor, Fmin, occurs. This tells designers the exact impedance they need to present to the device's input to achieve that lowest possible noise. It's usually not a perfect 50 ohm match, and Rn is the equivalent noise resistance. This parameter indicates how sensitive the noise figure is to changes in the source admittance or impedance as you move away from that optimum point, Ropt. A low Rn means the noise figure won't degrade too rapidly if the source impedance isn't perfectly set to opt, offering a bit more design flexibility or tolerance.
Okay, so Fremin is the best possible. Gamma opt is the impedance needed to get there, and Rn tells you how quickly it gets worse if you miss gamma opt.
That's a great summary. Designing low-noise amplifiers, therefore, involves complex trade-offs. Fremin doesn't necessarily occur at the standard system impedance, like 50 ohms, nor does it always align with the conjugate match impedance that would maximize the device's gain. You often have to make compromises. Do you match for lowest noise, using Fremin-opt, or for highest gain, or for best input return loss, closest to 50 ohms, or somewhere in between? These trade-offs are often visualized using noise circles plotted on a Smith chart, as shown in Figure 2.2 in our source material. A Smith chart is that familiar circular gradical tool used by RF engineers to visualize complex impedance values. These noise circles graphically represent contours of constant noise figure on the impedance plane, allowing designers to visually see the impact of different source impedance choices on the resulting noise figure. These are often used alongside gain circles derived from S parameters, which similarly show contours of constant gain, helping designers navigate those trade-offs.
So we understand what noise is, why it matters so much, and even the detailed parameters. But how do we actually put numbers to this invisible fluctuating phenomenon? What's the fundamental principle behind measuring noise figure in a way that's accurate and repeatable in the lab?
The foundation of most practical noise figure measurements rests on a really fundamental characteristic of linear two-port devices: noise linearity. What this means is that the output noise power of a device is directly and linearly dependent on the input noise power, or, equivalently, the temperature of the source providing that input noise. The source figure 3.1 illustrates this beautifully. It shows a theoretical plot of the device's output power versus the source temperature. It should be a straight line. If we can determine the slope of this characteristic line and establish a single reference point on it, we can then accurately find the amount of noise added internally by the device itself, often represented as not the added noise power. From this added noise, we can then easily calculate the noise figure F, or the effective input noise temperature.
So you need to measure the output at two different known input noise levels to define that line.
That's the core idea, yes. 2 points define a line. And a crucial point for ensuring this linearity holds true and for obtaining accurate measurements is that any automatic gain control, or AGC circuitry within the device under test must be deactivated. If the device's gain is constantly adjusting itself based on the input level, the linearity of the noise-power relationship is completely compromised, and that would lead to incorrect noise figure readings. You need the gain to be constant during the measurement.
Makes sense, keep the gain fixed. So if we need two known levels of input noise to determine that crucial slope, what exactly do we use in practice? How do engineers generate these precise known noise inputs in a repeatable way?
The key tool here, the workhorse, is a calibrated noise source. These devices are specifically designed to provide two known and distinct levels of noise power at their output, which we can switch between. The most popular type used today consists of a special low-capacitance semiconductor diode. This diode generates noise when it's reverse biased, with a specific constant current pushing it into avalanche breakdown mode. Companies like Keysight offer families of precision diode noise sources, such as their S&S series or the older N4000 series.
Avalanche breakdown sounds dramatic. That creates the noise.
It does. It's a controlled, stable, noisy state. When the diode in these sources is biased or turned on, it generates this broadband avalanche noise, which corresponds to a very high effective hot temperature, TH. This TO is typically around 10,000 Kelvin, sometimes higher depending on the design. When the bias current is removed and the diode is turned off, the output noise reverts to the simple thermal noise produced by its internal terminating resistor or attenuator, which corresponds to a cold temperature, TC. TC is usually designed to be close to the ambient temperature, typically around 290 Kelvin. These noise sources are also carefully designed with internal attenuators to provide a low standing wave ratio, SWR, which is a measure of how well their output impedance is matched to the standard 50 ohms. This helps minimize mismatch errors during measurements, which we know can be tricky. Modern noise sources are quite sophisticated. They even store their unique calibration data, including something called their excess noise ratio, in internal non-volatile memory. The measurement instrument can then read this data automatically.
Okay, you mentioned excess noise ratio, or ENR. What exactly is that?
ENR is the critical calibration parameter for a noise source. It's a calibrated measure of the noise source's output noise level difference between its hot and cold states, expressed in decibels, dB. Specifically, ENR in dB is defined as 10 times the logarithm of the ratio TH-TC V0, where TH is the hot temperature, TC is the cold temperature, and TO is our standard reference temperature of 290 Kelvin. It basically quantifies how much excess noise the source provides in its hot state relative to its cold state, normalized to TMU. It's a common misconception, by the way, that a 0 dB ENR means there's no noise. Actually, a 0 dB ENR signifies a temperature change of exactly 290 Kelvin between its on and off states, meaning TH-TC equals 290 K. It's not about the absolute noise level relative to TTB. ENR is the calibrated difference that allows our instruments to make accurate calculations.
Got it. ENR tells you the size of the noise step the source provides.
Precisely. And while diode noise sources absolutely dominate for most RF and microwave applications, say below 50 gigahertz or even higher now, due to their simplicity, stability, and broad bandwidth, Other types do exist, mainly for specialized or historical reasons. Hot and cold loads, for instance, are still used in high-precision calibration labs. These often involve immersing one termination in liquid nitrogen at about 77 Kelvin for the cold state and placing another in a precisely temperature-controlled oven for the hot state, perhaps at 373 Kelvin, 100 degrees C. They offer very high accuracy but are complex, slow, and definitely not portable. And historically, gas discharge tubes filled with argon or neon were used for millimeter wave noise generation, but these have largely been replaced by solid-state diode sources due to the diode's improved stability, smaller size, and much easier operation.
Okay, so diode sources are the main players now. With these noise sources providing precise hot and cold noise levels, what's the fundamental method that engineers rely on for making these critical noise figure measurements? Tell us about the Y-factor method you mentioned. It seems to be at the core of most analyzers.
The Y-factor method is, without a doubt, the dominant technique used in practice today and forms the basis for how almost all dedicated noise figure analyzers and many spectrum analyzer-based solutions operate. It's actually elegantly simple in principle. You connect your calibrated noise source to the input of the device under test, DUT. Then you use a power detecting instrument, like the receiver inside a noise figure analyzer, to measure the output noise power level coming out of the DUT under two conditions. First, with the noise source turned on in its hot state, TH. Let's call that measured output power level N2. Second, with the noise source turned off in its cold state, TC. Let's call that measured output power level N1. The ratio of these two measured output powers, N2 divided by N1, is defined as the Y factor. Y equals N2, N1.
Just the ratio of the hot output power to the cold output power.
Exactly. And the beauty of using this ratio is that the absolute power level accuracy of the power detector isn't as critical as its relative level accuracy, meaning its ability to precisely measure the change or ratio between N2 and N1. Modern noise figure analyzers excel here, using internal detectors that are incredibly linear over a wide dynamic range. Once you've measured the Y factor and you know the calibrated ENR of your noise source, which tells you TH and TC relative to T0, you can then determine the DUT's internal added noise power. From there, a relatively simple expression allows you to calculate the total system noise factor, phasis. This phasis includes the noise contributions of all individual parts of the system downstream from the noise source, including the measurement instrument itself, which is effectively treated as a second stage in the cascade following the DUT.
Now, one of the strengths of the Y-factor method, according to our source material, is that the device's gain is not actually needed to find that initial system noise factor, phasis. That must simplify things quite a bit for initial characterization.
Right. It absolutely does, which is one of the method's key strengths for getting a quick, basic measurement of the combined DUT plus instrument noise figure. You just need Y and ENR. However, the Y-factor method does have limitations. It's not ideal when the device's noise figure is much, much higher than the ENR value of the noise source you're using. In such cases, the DUT's own intrinsic noise tends to overwhelm or mask the relatively small change in input noise provided by switching the noise source between hot and cold. This causes the measured output powers N2 and N1 to be very close together, meaning the Y factor gets very close to 1, or 0 dB. Accurately measuring such small ratios can be challenging and prone to errors. Generally, the Y-factor method isn't recommended or might have reduced accuracy when the noise figure you're trying to measure is more than about 10 dB, maybe 15 dBs, above the noise source's ENR value. There are also specific temperature compensation equations, like equations 3.7 and 3.8 in the source, that instruments use automatically to account for the fact that the cold temperature, TC, of a solid-state noise source isn't exactly the standard 290 Kelvin, but usually tracks the ambient physical temperature.
Okay, so for those tricky, very noisy devices where the Y-factor method might struggle because Y is too close to 1, are there other ways to measure noise figure? Any alternative approaches?
Yes, there are a couple of alternative methods that are sometimes used, particularly for characterizing devices with high noise figures where Y factor might be less suitable. One is the signal generator twice power method. Here, you first measure the output noise power level with the DUT input terminated with a standard impedance load at approximately 290 Kelvin. Then you disconnect the load and connect a calibrated RF signal generator to the input. You adjust the signal generator's output power level until it produces exactly a 3 dBb increase, a doubling of power, in the DUT's total output power compared to the noise-only level. If you know the signal generator's output power level required to do this, and you know the noise bandwidth of your measuring device, you can calculate the noise factor. A key advantage here is that you don't need to know the DUT's gain. However, a significant disadvantage is that you do need to precisely know the effective noise bandwidth of your measuring device, and that can sometimes be tricky to determine accurately, especially if its filters aren't ideal.
Right, that bandwidth knowledge seems critical there. What's the other one?
The second alternative is the direct noise measurement method. This is perhaps simpler conceptually, but also has requirements. It's also useful for high noise figure devices. You simply measure the absolute output noise power of the device with its input terminated at approximately 290 Kelvin using a standard load. If you know the DUT's gain G accurately, and you know the noise bandwidth B of your measurement system accurately, and your power measurement, NOUT, is accurate in absolute terms, you can then directly calculate the noise factor using the relationship F equals NOUT, KT0BG. Unlike the twice power method, this approach requires knowing the DUT's gain and demands absolute level accuracy from your power detector. Both of these alternative methods really emphasize the crucial role of accurately defining and knowing the measurement bandwidth.
Okay, so different methods for different situations, but Y factor seems dominant. Now, you mentioned that the Y factor method, and indeed these others, typically give us the total system noise factor, that is, the noise figure of the DUT plus the measurement system itself acting as a second stage. How do we isolate the noise figure of just our actual device under test, DUT? How do we accurately correct the measurement system's own noise contributions, especially if the DUT has low gain or we need high accuracy?
That's a critical step, absolutely, especially, as you say, for low-gain DUTs, where the second stage, the instrument contribution, isn't negligible, or whenever the highest measurement accuracy is required. This process is often called applying a second-stage correction or measuring the corrected noise figure and gain. Its purpose is to precisely remove the measurement system's own noise contribution from the overall measurement result. It cleverly leverages Fries's cascade equation, but sort of runs it in reverse to back-calculate the DUT's true noise figure, F1. Here's how the system calibration and measurement process works, and this is something that modern noise figure analyzers automate beautifully. 1. First, you perform a calibration step. You measure the measurement system's own noise factor. Let's call it F2, representing the second stage. You do this by connecting the calibrated noise source directly to the measurement system's input, with no DUT, and performing a standard Y factor measurement. The instrument stored this F2 value. It also measures its own gain during this step. 2. Next, you insert the DUT into the system, between the noise source and the measurement instrument's input. 3. Now, you perform the measurement again. You measure the new output noise levels with the noise source turned on, let's call this N2, and turned off, N1. 4. From these measurements, N2 minute and 1, and the known ENR, the instrument calculates the overall system noise factor, FIRSILIS, using the Y factor method again. This FIRSIS represents the noise factor of the DUT F1 cascaded with the instrument F2. 5. Crucially, the instrument also calculates the DUT's gain, G1. It can do this by comparing the change in noise power between the hot and cold states with the DUT inserted versus during the calibration step, essentially using the noise source as a relative signal source. Equation 312 in the source shows one way to calculate this gain. 6. Finally, using the measured FIRSIS, the stored F2 from calibration, and the calculated G1 of the BUT, the instrument uses a rearranged version of FIRSIS cascade equation, specifically F1 wheel SMARSIS, F2 to 1 G1, as shown in equation 311, to solve for F1. This F1 is the actual corrected noise factor of the DUT alone.
Wow, okay, that sounds quite involved with multiple steps and calculations. It's really incredible how modern noise figure analyzers automate all of that complex multi-step calculation, making highly accurate, corrected measurements far more accessible and faster than they would ever be manually. It's a huge time saver for engineers, I imagine.
Oh, absolutely. They handle all the intricate math, the storing of calibration data, and the corrections completely in the background. It transforms a potentially tedious and error-prone process into a push-button measurement. Now, even with all these precise methods and corrections, we have to remember that noise itself is inherently random. It's a series of random electrical impulses, not a steady DC level. How does this fundamental randomness impact our measurements, and what does the term jitter mean in this context? Yeah, how do you measure something that's constantly fluctuating?
You've hit on a core challenge in any noise measurement. Because noise is, by definition, a random or stochastic phenomenon, a series of unpredictable electrical impulses arriving at random times. Any measurement we take over a finite period of time can only ever be an average value. The goal is to find the true mean noise level, which represents the average power. However, the difference between the average we measure over a finite time window and the theoretical true long-term mean will constantly fluctuate from measurement to measurement. This fluctuation, this uncertainty or variation in the measured average, gives rise to what we call jitter, which is essentially a repeatability error in our noise measurements. If you take measurements quickly, one after another, the reading will bounce around slightly.
So that's why sometimes the readings seem to jump around a bit on the screen.
Precisely. As Figure 3.2 in our source material illustrates conceptually, the standard deviation or expected fluctuation in our measurement, the jitter, is inversely proportional to the square root of the measurement time and also inversely proportional to the square root of the measurement bandwidth. So deviation scales like 1 time bandwidth. This means that to get a better, more accurate, more stable average and reduce the impact of jitter, we need to do two things. First, increase the averaging time, essentially, measure for a longer duration, allowing more random events to contribute to our average, smoothing out the short-term fluctuations. Second, if possible within the constraints of the DUT, we can increase the measurement bandwidth as long as it remains narrower than the DUT's own operational bandwidth, of course. A wider measurement bandwidth includes more noise power and thus more independent noise events per unit of time, which again leads to a more stable, truer average more quickly. It's all about gathering enough statistical data, either by measuring longer or wider in frequency, to smooth out the inherent randomness and get a reliable reading of the average noise power. Modern instruments allow you to control averaging to trade off measurement speed versus jitter reduction.
Okay, we've covered amplifiers and general two-port devices. But mixers and receivers are specifically designed to convert signals from one frequency to another, usually from RF down to an IF. Does this frequency conversion process introduce new complexities when we're trying to measure noise figure, or do the basic principles just universally apply?
That's a really important area. While the general noise figure relationships and definitions we've discussed do still apply fundamentally to frequency converters, these devices, mixers, down converters, up converters, entire receivers, which inherently include mixing, introduce several additional characteristics and potential pitfalls that significantly affect noise figure measurements and require careful consideration. Often, even the noise measurement system itself might use internal mixing to extend its own frequency range, so these challenges can sometimes pop up even in the measurement setup itself, not just the DUT.
So what are some of these unique challenges with converters?
Well, first, consider loss versus gain. Amplifiers typically have gain, meaning their linear gain value is greater than 1. Passive mixers, however, which are very common, inherently have conversion loss, meaning their effective gain is less than 1, or negative in dB. All the noise figure equations, including Fries's cascade equations, still apply perfectly well, but this loss has significant implications. For instance, in the cascade noise figure equation, Fries's equals F1 plus F2 to 1 G1 plus, if the first stage, the DUT, is a lossy mixer, then G1 is less than 1. Dividing by a number less than 1 actually amplifies the contribution of the second stage, F2.1. This means that for a DUT with loss, the noise contribution of the measurement system, the second stage, can become major and absolutely must be accurately calibrated out using the second stage correction technique we just discussed. Also, for high noise figure passive mixers, where F1 itself is large, often close to the conversion loss, the Y factor measured can be quite small, close to 1, which, as we know, can increase measurement uncertainty. Using high ENR noise sources can help here by providing a larger difference between N2 and N1, thus a larger Y factor, improving the signal-to-noise ratio of the measurement itself.
Okay, so loss on the first stage makes the next stage's noise much more important. What else?
A potentially significant challenge is LO noise. Receivers and mixers rely on a local oscillator, or LO, signal to perform the frequency conversion. If this LO signal itself contains noise, particularly noise at frequencies offset from the main LO tone by the IF frequency, i.e. at FLO and EFIF, that noise can mix with the clean LO tone and get converted down into the IF band, adding directly to the system's overall noise figure. It acts like unwanted signals coming in the RF port. The magnitude of this effect can vary greatly depending on the mixer type, e.g. single balanced versus double balanced, and critically the spectral purity or phase noise of the LO source itself. In fixed-frequency LO systems, this LO noise contribution can often be mitigated by adding a narrow bandpass filter on the LO port of the mixer, designed to pass only the desired LO frequency but reject noise out in the sidebands at FLO, FLF, and also block noise conversions involving higher harmonics of the LO. Sometimes low-pass filters are used too.
So you need a clean LO for a good noise figure measurement. Makes sense.
Definitely. Then there's LO leakage. Even in well-designed mixers, some amount of the powerful LO signal might leak through to the output, the IF port, of the mixer or converter. While this might be perfectly acceptable for the intended application of the device, during a sensitive noise figure measurement, this leaked LO signal can be strong enough to overload the sensitive input stages of the noise measurement instrument. Or it could potentially mix with other signals or noise within the instrument itself, creating spurious products that corrupt the measurement. This is especially likely if the measuring system has a broadband amplifier right at its input. A common solution here is to add a filter at the instrument's input, maybe a notch filter at the LO frequency, or a low-pass filter if the IF is much lower than the LO to suppress the leaked LO signal while allowing the desired IF noise signal to pass through unimpeded.
Filtering seems to be a recurring theme here.
It often is in RF measurements. And finally, related to the mixing process itself, we have to contend with unwanted responses, sometimes called spurious responses. The desired RF frequency band isn't always the only band that gets converted down to the IF by the mixer. Other unwanted frequency bands can also convert if signals or noise are present at those frequencies at the RF input port alongside the desired signal. The most famous of these is the image response. If your desired signal is at FRF and your LO is at FLO and your IF is FOF FLO, then there's another frequency, FIMAGE FLO or FEF, the one that wasn't FRF, that also mixes with the LO to produce the same IF output. So noise at the image frequency gets converted down just as efficiently as noise at the desired RF frequency in many simple mixers. Beyond the image, there can also be harmonic responses involving multiples of the LO frequency, like 2FLO anaphylonoma, 3FLSs, 3FLO FIF, various other spurious mixing products, and even direct IF feed-through from input to output. While many complete receivers incorporate filtering, like preselector filters, to minimize these unwanted responses before the mixer, many standalone mixer components will exhibit one or more of these responses quite strongly. This means they can potentially convert additional noise from these unwanted frequency bands into the IF band, artificially inflating the measured noise figure if not accounted for. The source's figure 3.3 beautifully illustrates these potential conversion mechanisms and why they complicate measurements.
Wow, okay. Image noise is a big one. This brings up the common distinction you often hear about. Double sideband, DSB versus single sideband, SSB mixers. How does this difference impact noise figure measurements, particularly when selecting the right measurement approach or interpreting the results?
This distinction is absolutely crucial for accurate measurement and correct interpretation, especially when dealing with mixers or instruments containing mixers. A double sideband DSB mixer is one that, by design or lack of filtering, converts noise from two main frequency responses, typically the upper sideband, USB, often defined as FLO plus EF, and the lower sideband, LSB, FLO, FIF, down into the same IF band. It's sensitive to noise in both sidebands simultaneously. Now, if such a DSB mixer is incorporated within the noise measurement system itself, perhaps in its front-end down converter, this second response will inherently create an error in noise figure measurements if you're trying to measure an SSB device. Why? Because the instrument is effectively collecting noise from twice the expected signal bandwidth. It's getting noise from both the signal channel and the image channel. To correct for this, when measuring an SSB DUT with a DSB instrument, a +3 dB correction factor is often mathematically applied to the measured noise figure result. Ideally, though, filtering should be used at the RF port of the measurement system's internal mixer to eliminate one of these sidebands, usually the image, ensuring that true single sideband SSD measurements are made by the instrument.
Okay, so the instrument might need correction or filtering? What if the DUT itself is DSB?
Right. Now, if a DSB mixer is the device under test, the situation is slightly different. Usually, the user testing such a device still wants to know its equivalent SSB noise figure. This is because most communication systems using such a mixer would employ filtering before the mixer to select only one sideband, either USB or LSB, for the actual signal transmission. For passive mixers without significant LO noise contributions, this equivalent SSB noise figure is often expected to be close to the mixer's conversion loss, measured with a simple continuous wave, CW signal. There are two primary ways to achieve this equivalent SSB noise figure measurement for a DSD DUT. You can use an input filter placed before the DUT to select only one sideband, either USB or LSB, and reject the other before the noise even enters the mixer. The measurement then directly yields the SSB noise figure, too. Or you can measure the mixer without an input filter, so it responds to noise in both sidebands, and then apply the +3 dB correction factor mathematically to the resulting measured DSB noise figure to estimate the SSB value. However, it's important to be aware of the accuracy implications with both methods. An input filter will introduce its own insertion loss, which must be carefully accounted for and removed from the measurement, and the +3 dB correction factor relies on the critical assumption that the mixer's response, its conversion loss and noise contribution, is perfectly equal in both the USB and LSB, which isn't always strictly true in real devices.
So filtering is probably more accurate if you can manage the loss calibration.
Generally, yes. Using an input filter provides a more direct and potentially more accurate SSB measurement if the filter characteristics are well known. But it's worth noting one final point. Some specialized frequency converters, such as those found in radiometers used for detecting very faint thermal noise signals in radio astronomy or remote sensing, are actually intentionally designed to utilize both main sideband responses, USB and LSB. They want to collect as much noise power as possible from the source they are observing. In these specific cases, it's desirable to know the true DSB noise figure of the device, and therefore no plus 3 dB correction is applied and no input filter is used. Or rather, the input filter is wide enough to pass both sidebands. The resulting measured noise figure is explicitly understood and specified in DSB terms. The engineer's intended application for the device ultimately defines the correct measurement strategy and interpretation.
Okay, we've really dug into the theory, the challenges, the corrections. It's complex. Let's turn our attention now to the specific tools that engineers use in the lab to actually tackle this challenge. What are dedicated noise figure analyzers, NFAs, and how do they streamline this whole process?
Dedicated noise figure analyzers, NFAs, like Keysight's NFA X-Series instruments, really represent the pinnacle of specialized instrumentation designed specifically for this task. You can think of an NFA at its core as a highly accurate sensitive receiver combined with a precise power detector and integrated control circuitry designed to automatically power and switch a calibrated noise source. These instruments are engineered from the ground up to automate the entire noise figure measurement process we've been discussing. You connect the DUT, you connect the noise source, you tell the NFA the ENR calibration data for that source, often read automatically from the source's memory, and the NFA internally performs the Y-factor measurements, applies the necessary temperature compensations, calculates the system noise figure, performs the second stage correction using its stored calibration data, and calculates the DUT's gain. They typically provide real-time swept frequency displays of both the corrected noise figure NFF and the gain of the DUT, often with advanced features like markers, limit lines for pass-fail testing, and sophisticated averaging options to manage jitter. They make characterizing devices across a wide frequency range incredibly efficient.
So they're the all-in-one purpose-built solution. But many labs already have general-purpose analyzers, like spectrum analyzers on the bench. Can these versatile powerhouses also be pressed into service for measuring noise figure, or are they too general-purpose for such a specialized task?
Oh, absolutely they can. Signal analyzers or spectrum analyzers, such as Keysight's X-Series signal analyzers like the EXA or PXA, are quite commonly used for noise figure measurements, particularly in labs that need a multifunctional instrument that can do many things beyond just noise figure. Often this is done with the addition of specialized noise figure measurement application software, which might run on the instrument or an external PC controller, that guides the process and performs the calculations. With this software and a compatible noise source, they can perform noise figure measurements using any of the methods we've discussed, including the Y-factor method, or potentially the signal generator twice power, or direct noise measurement methods if needed, especially for characterizing devices with high noise figures.
What are the pros and cons compared to a dedicated NFA?
Well, the advantages include their inherent multifunctionality. You get a spectrum analyzer too. Often excellent sensitivity, especially in higher-end models, and precisely defined, often variable resolution bandwidths, RBWs. This variable RBW is very useful for accurately measuring narrowband devices, where you need the measurement bandwidth to be narrower than the DUT bandwidth. They can achieve very low measurement uncertainties, often negligibly degraded from the fundamental capabilities imposed by the noise source uncertainty itself. Many modern signal spectrum analyzers can have dedicated noise figure measurement personalities or applications added as options, making them perform very similarly to dedicated NFAs for many tasks. The main potential downside might be slightly less optimized workflow or potentially slightly slower measurement speed compared to a dedicated NFA in some cases, but they are extremely capable.
Okay, so spectrum analyzers are a very viable option. What about network analyzers, VNAs, which are often the go-to instruments for measuring S parameters, gain, loss, reflection coefficients? Can they also get in on the noise figure game? Or are they strictly for characterizing how signals pass through a device?
Yes, network analyzers, particularly modern ones, often offer noise figure measurement capabilities as well, in addition to their core S parameter, and sometimes gain compression or distortion measurements. This can be really advantageous for obtaining a comprehensive multi-parameter view of a device's performance using a single instrument connection. You get gain, match, and noise figure. However, because their internal receiver architecture is typically optimized primarily for network measurements, ratio measurements of coherent signals, there can be some performance limitations or considerations when using them for noise figure applications, which involve measuring absolute noise power levels. Often, the receivers inside a VNA might be of the double sideband, DSB type, meaning they effectively measure noise at two frequencies, signal and image, simultaneously. An internal correction, like that plus 3 dB factor, is then applied mathematically. As we discussed, this can introduce errors, particularly if the device's noise figure or gain isn't constant across that relatively wide measurement bandwidth encompassing both sidebands. Also, when using the narrower measurement bandwidths available on some VNAs, needed for narrowband devices, the unused frequency spectrum between the upper and lower sidebands doesn't contribute useful information to the noise measurement, potentially requiring longer measurement times to achieve the same level of jitter reduction compared to an SSB receiver architecture like in an NFA or SA.
And you mentioned the S parameter issue earlier.
Right. And it's critical to reiterate that while network analyzers excel at measuring S parameters, which describe how signals travel and reflect within a device, S parameter data alone isn't sufficient to fully correct noise figure uncertainty due to mismatch effects in a cascade. S parameters help correct for gain variations due to mismatch, but they don't fully account for how that impedance mismatch actually alters the fundamental noise generation processes within subsequent stages or at the DUT input itself, unless you have the full noise parameters, a fan, UOPT, RN, of the device being measured. Standard VNAs, by themselves, don't provide these noise parameters.
Okay, so if S parameters aren't enough for really deep dive into noise behavior, particularly for device modeling or designing for optimal noise match, what instrument helps us find those crucial noise parameters, a FEM, UOCT, and RN? This sounds like the absolute pinnacle of device noise characterization.
It absolutely is the pinnacle for in-depth active device noise characterization. For that, we need noise parameter test sets, MPTS. These are highly specialized measurement setups, not usually a single box, but a system. They are typically used in conjunction with dedicated control software, a vector network analyzer, VNA, to measure S parameters and impedances accurately, and a noise analyzer, which could be a dedicated NFA or a capable SA with noise figure application. The core mechanism involves an automated impedance tuner placed between the noise source and the DUT input. This tuner, under software control, systematically presents a wide range of different known complex source impedances to the DUT's input. The test set also provides the necessary DC bias to the active device, like a transistor, and couples the noise source through the tuner to allow for noise figure measurements to be made at each of these varying source impedances. The vector network analyzer simultaneously measures the actual complex source impedance being presented by the tuner at each step, and also usually measures the DUT's S parameters under those conditions. From this extensive dataset noise figure measured versus source impedance, the control software can accurately calculate and extract the full set of noise parameters, FEM, REOPT, and RN, of the device, often as a function of frequency and bias condition.
So it's like mapping out the noise performance across all possible input conditions.
Exactly. These measurements are significantly more complex and slower to perform than a conventional single noise figure measurement at 50 ohms. But they yield invaluable design parameters that are absolutely crucial for engineers designing low-noise amplifiers or modeling transistor behavior. This is the kind of data you often find presented on datasheets for low-noise transistors. These sophisticated noise parameter test sets are typically not used for characterizing standard 50 ohm or 75 ohm matched components or systems, where the source impedance is usually fixed by the application anyway. They're really for deep device-level characterization.
Right, for the component designers mostly. Now, just to round things out, can simpler, more fundamental devices like basic power meters and true RMS voltmeters also be used for noise figure measurements, perhaps in a pinch, or for simpler setups, or are they really out of their league here?
They can be used, theoretically, but with significant caveats and a lot more effort and potential for error compared to the dedicated instruments. Power meters, like Keysight's EPM series, often used with thermal or diode sensors, and true RMS voltmeters, capable of accurately measuring non-sinusoidal AC signals like noise, are fundamentally level measuring devices. They can be employed with any of the methods we've discussed, Y factor, twice power, direct. However, a major drawback is that they are inherently broadband devices. They measure power across a very wide frequency range. Therefore, they absolutely require external, well-characterized bandpass filters to be placed before them to define the specific measurement bandwidth B needed for the noise figure calculation. Such filters usually fix the measurement frequency as well, restricting you to single frequency measurements unless you have a bank of filters.
And sensitivity must be an issue.
That's the other big problem. The sensitivity of standard power meters and voltmeters is generally quite poor compared to dedicated noise receivers. Noise levels are often very low. So the receiver or DUT being measured usually needs to provide a very high level of gain itself to make the noise levels detectable by these basic instruments. If you try to add extra amplification externally just before the power meter or voltmeter to boost sensitivity, extreme care must be taken to manage potential gain drift due to temperature changes, and also to avoid creating unwanted oscillations within the high gain setup, as these can easily introduce huge errors into the noise measurement. So while possible perhaps for very high noise figure devices or in highly controlled, specific scenarios, using basic power meters or voltmeters for noise figure is far less convenient, generally less accurate, requires manual calculations and careful filtering, and is typically reserved for situations where more sophisticated instruments aren't available or practical. Outro.
So what's the big picture here then? We've really gone on quite a journey, haven't we? From the tiniest, spontaneous electrical fluctuations that are the very essence of noise, through its critical and often silent impact on virtually every communication system we rely on today. We've understood its precise and foundational definition thanks to the work of Harold Freese back in the day. We've grappled with the sometimes confusing complexities of multi-stage systems, cascaded noise, gain types, and impedance mismatches. And we've explored the sophisticated methods and the impressive array of instruments that engineers use to measure and ultimately mitigate this ever-present challenge.
This deep dive really reinforces that a thorough understanding of noise figure isn't just some, academic exercise for electrical engineers sitting in ivory towers. It's absolutely fundamental to the design and optimization of everything. From the most reliable deep space satellite links that bring us global communication and navigation, to the efficient, high-capacity broadband networks that power our homes, our businesses, our streaming habits, everything. It's about meticulously optimizing performance, managing sometimes astronomical costs, remember that satellite dish example, and constantly pushing the boundaries of what's possible in a world that's just increasingly reliant on clear, uninterrupted, and robust signals. Noise figure in many ways is the silent enabler or the silent killer of our connected world. Understanding it is key.
That's a great way to put it, the silent enabler. And as technology continues its relentless march, miniaturizing components, pushing frequencies ever higher, demanding ever faster, more reliable wireless communication everywhere. And as we look towards potentially radically new paradigms on the horizon, how might future innovations, perhaps things emerging from quantum computing research, or maybe breakthroughs in groundbreaking new material science, how might they fundamentally change how we perceive, measure, and maybe even, dare I say, eliminate noise altogether? Could we completely reshape our digital future by sidestepping this age-old adversary? And if so, what new noise figures, what new metrics might we need to invent then to characterize technologies we can only just begin to imagine today? Something to ponder perhaps until our next deep dive.